Okay guys, in this video we are going to be talking about phase transitions, and what we'll do is we'll talk a little bit about intermolecular interactions and their impact on phase transitions, and then we're also going to talk about the thermodynamics of phase transitions as well. So here's a list of phase transitions that we've discussed previously, and what I'll point out is that certain phase transitions, the ones where you go from a more condensed phase to a less condensed phase, are endothermic. So for example, sublimation, fusion or melting, vaporization, these all involve breaking intermolecular forces. So as a consequence of having to break an interaction, it leads to an endothermic process. Whereas the opposite phase transitions, so deposition, freezing, and condensation, where you're going from a less condensed phase to a more condensed phase, you're forming intermolecular interactions, which is an exothermic process. Here's some graphical examples of phase transitions. So when our bodies sweat, the liquid evaporates into the atmosphere. That's an endothermic process. That's what helps you stay cool, because it's endothermic. Over here we've got some iodine crystals, these solid purple crystals, and you can see the purple vapor above the solid, so this is sublimation. This is also an endothermic process. And then the panels down here, they denote the melting of ice, so you've got ice at negative 12 degrees. At 0 degrees you have an equilibrium between ice and the liquid water. And then at higher temperatures you have the liquid phase being stable. This is also an endothermic process when you melt the ice. On this slide I'm introducing the concept of vapor pressure. And so what I'd like to do is to draw a little diagram here. Imagine that you've got a sealed container of liquid. Eventually the liquid will come into equilibrium with the vapor phase at a given temperature. And after that equilibrium has been established, the pressure of the vapor is called the vapor pressure of the liquid. Okay, so all liquids have a vapor pressure. The vapor pressure depends upon the substance that you're talking about because it's related to intermolecular interactions. The stronger the intermolecular interactions, the lower the vapor pressure. The weaker the intermolecular interactions, the higher the vapor pressure, the greater the tendency for the liquid to vaporize. The vapor pressure also depends upon temperature. Okay? And so as you increase the temperature of a substance, its vapor pressure also increases. And so here's a couple of diagrams illustrating vapor pressure. Let's focus in on water. You see that at low temperatures, water has a low vapor pressure, but as you increase the temperature of the water, the vapor pressure steadily rises. This horizontal line here represents atmospheric pressure, so the external pressure set equal to 1 atmosphere. At that particular temperature, when the vapor pressure of the liquid equals the external pressure, you're going to get boiling to occur. And different substances, they have different vapor pressures. Now they all increase with temperature, but where you start at a given temperature depends on the substance, and it depends on the intermolecular interactions between the molecules of that substance. So in ethylene glycol, you have strong interactions between the molecules, so the vapor pressure is very low, even at moderately high temperatures. But for something like ethyl ether, where you have weak interactions between the molecules, you see that you already start, even at low temperatures, at a high vapor pressure. And so consequently, it doesn't take that significant of an increase in temperature to get the ethyl ether to start boiling. The panel down below illustrates this idea in terms of the kinetic energy of molecules. And so at a low temperature, we have this distribution here where very few molecules have sufficient kinetic energy to escape the liquid phase. But as you increase the temperature of the liquid, that changes the distribution, and there's going to be a higher fraction of molecules that have enough kinetic energy to get into the liquid phase. Therefore, you're going to have a higher vapor pressure. On this example problem, we're being asked to to compare vapor pressures. So in part I of part A, we're being asked to compare the vapor pressures of CO2 and SO2. CO2 is a polar molecule, and sulfur dioxide is a nonpolar. Carbon dioxide is a nonpolar molecule, and sulfur dioxide is a polar one. So the sulfur dioxide is going to have, in addition to the London dispersion interactions, it's also going to have dipole-dipole interactions. And so we are going to say that there are stronger intermolecular forces in the SO2, therefore it's going to have a lower vapor pressure. CO2 is going to have weaker intermolecular forces, therefore it's going to have a higher vapor pressure. For the hydrocarbons, okay, these are all nonpolar species in part B. And so we're only thinking about the London dispersion interactions here. The one with the strongest intermolecular interactions is going to be the butane. Butane has more electrons, therefore London dispersion is going to be a larger effect. Therefore, it's going to have the smaller vapor pressure. That's going to be followed by the propane, which is going to be in between, so it's going to have a moderate vapor pressure. And then the highest vapor pressure is going to be from the ethane, because it is the smaller of the molecules. It's smaller, so it has weaker intermolecular forces. That means it's going to be easier to vaporize. Okay? So in terms of vapor pressure, the ethane is going to be the largest, and the butane is going to be the smallest. Looking at part C, okay, they give us two molecules. I'm going to go ahead and draw the structures. We have methyl chloride that we're comparing to ethanol. Okay. The methyl chloride, you see, has a very high vapor pressure, 1490 millimeters of mercury, whereas the ethanol, by comparison, has a low vapor pressure of 42 millimeters of mercury. Why is that? Well, you see the oxygen-hydrogen bond in the ethanol. That means that the ethanol is capable of participating in hydrogen bonding, which is a very strong intermolecular interaction. Therefore, because there are stronger intermolecular forces present in ethanol, you're going to expect it to have a lower vapor pressure, which it does. Part D is similar in the sense that we have a number of molecules to look at. Their structural formulas are given there, and they want us to compare which ones are going to have, let's say, which one has the highest vapor pressure and which one has the lowest. And so in this example, we notice that the ethylene glycol has two OH groups, okay, each of which is capable of participating in multiple hydrogen bonds. And so I would expect the ethylene glycol to have the strongest intermolecular forces, and therefore it's going to have the lowest vapor pressure. The diethyl ether, on the other hand, is a nonpolar species. I would expect it to have the weakest intermolecular forces, and therefore it would have the highest vapor pressure of all of them. In this this diagram is just meant to illustrate the effect, the boiling point effect. I mostly wanted to introduce the distinction between the boiling point of a liquid and its normal boiling point. So the term normal boiling point applies when the external pressure is 1 atmosphere, and you raise the temperature of the substance until its vapor pressure equals 1 atmosphere. The corresponding temperature is called the normal boiling point. However, if you were to change the external pressure, let's suppose that we were to do an experiment where we boiled water at an external pressure of 27 kilopascals, you would find that the boiling point of water is much lower than 100 degrees Celsius. It would be between, say, 65 and 70 degrees Celsius at that lower external pressure. So normal boiling point means the external pressure is 1 atmosphere, but the boiling point of a liquid depends upon the external pressure. So in this series of questions, why does water boil at 100 degrees Celsius in New Orleans and only 95 degrees Celsius in Denver? Well, it's because at higher altitudes, the atmosphere is thinner. The external pressure is going to be lower in Denver compared to New Orleans. Therefore, you don't have to raise the temperature of water quite as high to reach the external pressure. And so it's going to boil at a lower temperature. The other two questions are just variations of that same idea. So I'll leave those for you to think about as conceptual exercises. We're going to turn our attention next to the Clausius-Claperyon equation, which relates the vapor pressure of a liquid to its temperature. Okay? There's two versions of the equation. There's the linear form, and then there's what I call the two-point form. Let me just explain why I call the linear form the linear form. If we take the equation and imagine plotting the natural log of the vapor pressure along a y-axis, and then we'll plot along the x-axis, we're going to plot 1 over the temperature for that vapor pressure. So this is going to be our x-coordinate. We can call this a value m, and then the constant b, we'll call that lowercase b, and you'll probably recognize this as the form of a line, right? If you were to plot y as a function of x, in this case, because we're talking about vaporization, delta H is always positive, so the slope m is always negative. We're going to get a downward sloping line where the slope is equal to minus the enthalpy of vaporization divided by the gas constant. So this is why I call it the linear form, because you can make it look like a line when you plot it. And then the two-point form just refers to the fact that any 2 points along a line are connected to one another through the linear equation. So if you were to call this 1 over t1, and this is 1 over t2, this would be the natural log of p1, the natural log of p2. These values are all related to one another through this two-point Clausius-Claperyon equation. Okay? And this is actually the one that we're going to use in our problem solving, as we'll see in this example. So here we're being asked to estimate the vapor pressure of water at 85 degrees Celsius, given that the boiling point at a pressure of 1 atmosphere is 100 degrees Celsius. So at 1 atmosphere pressure, or so for a vapor pressure of 1 atmosphere, the temperature corresponding to that would be 373 Kelvin. Or I should say, at 373 degrees Kelvin, the vapor pressure of water is 1 atmosphere. They want us to calculate the vapor pressure of water at a different temperature. 85 plus 273 is 358 Kelvin. We expect that if you lower the temperature, you're going to lower the vapor pressure. Okay, and so let's calculate the value of that vapor pressure. We need to use the two-point Clausius-Claperyon equation. Okay. We know the two temperatures, we know one pressure, and we know the enthalpy of vaporization. That's the 40.7 kilojoules per mole. So we need to exponentiate both sides and solve for P2. So after some algebra, get this result. And we can plug in the numbers. So that's minus 40.7 kilojoules per mole. And then for the gas constant, we want to use matching units. So 8.314 times 10 to the minus 3, that'll be kilojoules per mole Kelvin. for R. And then we have the two temperatures, 1 over 358 minus 1 over 373. And so we can run this through our calculator, starting with the temperatures first. 1 divided by 358 minus 1 divided by 373. Take that times 40.7 divided by 8.314 times 10 to the minus 3. We want to add in the minus, or we want to multiply the minus sign. And then we're going to use the anti-logarithm button on our calculator to calculate the exponential. And that's multiplied by 1 atmosphere. And I'm getting a value of 0.577 ATMs out of this calculation. So as you lower the temperature, the vapor pressure goes down. The Clausius-Claperyon equation allows you to calculate that. You need to know the enthalpy of vaporization of the liquid in order to use the Clausius-Claperyon equation. You're going to find that this problem here involving carbon disulfide is exactly the same, so it's solved in exactly the same way. The only thing that changes are the vapor pressures involved and the enthalpy of vaporization. It's a different liquid. This problem here involving the diethyl ether is a little bit different. We're being asked to calculate the enthalpy of vaporization. So do a little bit of algebra first. So here's the equation again. This time they give us 2 temperatures and 2 pressures, and they want us to find the enthalpy of vaporization. So I'm going to solve for that first, just using some algebra. And then you want to substitute in the numbers. So I'm going to do minus 8.314 times 10 to the minus 3 kilojoules per mole. We'll take that times the natural log. We're going to call 400 P1, and 18 degrees Celsius is T1, and then the 760 will be P2, and 35 degrees Celsius will be T2. So we want P2 over P1, so that's going to be the natural log of 760 divided by 400. And then all of that is divided by 1 over T2, which is going to be 308 Kelvin minus 1 over 291 Kelvin. Okay, so I'm going to start the calculation on my calculator with the pressures. So I'll take 760 divided by 400, and then I'm going to take the natural log of that. Let's see here, 760 divided by 400. Take the natural log. Now I'll multiply by the gas constant. I'm going to go ahead and multiply in that negative. And then I'm going to divide by the quantity, 1 divided by 308 minus 1 divided by 291, close quantity. And I'm getting 28.1, and that's going to have units of kilojoules per mole. Okay, so that'll be the enthalpy of vaporization. It should be positive because vaporization is an endothermic process, and so that's one check that you didn't make a mistake with the signs or getting the temperatures switched out. When I paused there for a moment, that's what I was checking to make sure I didn't make a mistake when I input the temperatures. Yeah, so that's how you do this problem. It looks like this one is identical in the sense that they give you 2 pressures, 2 temperatures, and they want you to calculate the enthalpy of vaporization for the selenium tetrafluoride. here in this concept, it's really just an illustration of Hess's law for phase transitions. And so we're looking at the fusion reaction, solid going to liquid, vaporization, liquid going to gas, and the heat of sublimation, solid going to gas. If you imagine adding these two equations together, the waters would cancel out, and you would have the sublimation reaction. So sublimation can be thought of as the sum of fusion and vaporization. As a consequence of that, the enthalpy of sublimation is the enthalpy of fusion plus the enthalpy of vaporization. This curve is illustrating what happens to the temperature as you add heat. So if you imagine adding incremental amounts of heat, what happens to the temperature of a substance? Well, if you had something like ice starting at -10 degrees Celsius and then you added a little bit of heat, that's going to cause the temperature to increase. And the increase, the amount by which the temperature of the ice will increase, is related to the mass and the specific heat. So we'll remember this formula from the thermochemistry chapter. The amount of heat added is related to the delta T, and the proportionality factor is the mass times the specific heat. This is the heat capacity of your sample. Well, once you get to the melting point of the ice, you'll notice that as you add more heat, the temperature doesn't change. This is often called the latent heat. And this corresponds to the change in the enthalpy of the phase transition. So the amount of heat that you add to convert the solid to the liquid is related to the number of moles of sample that you have times the enthalpy of the phase transition. Well, once you melt all of the solid and you have all liquid, then you start heating up the liquid. So you're adding in heat, and the temperature increases linearly according to this relationship where you're using the specific heat now of the liquid, not the solid. At a certain point, you get to the boiling point of the liquid. At that point, you continue to add heat, but then you notice that the temperature doesn't change. Again, it's a constant temperature. As you're adding heat, what you're doing is you're converting all of the liquid to the water vapor. And then after you've boiled off all of the liquid water, then what you do is you start heating up the steam. And again, as you add heat, the temperature is going to linearly grow according to this relationship, but instead of using the specific heat of liquid water, you would use the specific heat of water vapor. And I guess the point that I need to mention is that the ice, the liquid water, and the steam, they all have different specific heats. Okay, and so the slope of these lines would actually be different. And so in this example, we're being asked to think about refrigeration. And so we've got our refrigerator here works by evaporating liquefied dichloro-difluoromethane. How many kilograms of this liquid must be evaporated to freeze a tray of water at 0 degrees Celsius into ice? The mass of the water is 525 grams, and the heat of fusion of ice is 6.01 kilojoules per mole. And then they give us the heat of vaporization of the dichloro-difluoromethane. So let's think about this in terms of the phase transition for the ice. Okay, so we'll look at this idea here, that the heat for the phase transition is going to be the number of moles of the water that we have times the enthalpy of, I guess we would want to use, we'd want to use the, it would be minus the enthalpy of fusion, all right, because we're not fusing, we're doing the opposite, we're freezing. And so it would be minus the enthalpy of fusion. So we've got the mass divided by the molar mass times minus the enthalpy of fusion. So we've got 525 grams of water, I believe, divided by 18.02 grams per mole. Take that times the negative 6.01 kilojoules per mole. So we need to pull 175 kilojoules out of the water. Okay, so that's the heat for the that's the heat that we need to let's see. Yeah, we need to pull that much heat out of the water in order to get it to freeze. Now, that heat is going to be supplied by the evaporation of the difluoromethane. And so the heat for that process will be equal to the number of moles of the difluoromethane. And we're going to take that times the enthalpy of vaporization of that substance. And so here they want to know what is the mass. We'll need to calculate the molar mass, and they've given us the vaporization. And so we need to equate this amount of heat with this heat here. Okay, so we're going to solve for the mass. It's going to be equal to Q times the molar mass divided by the enthalpy of vaporization. And so we're going to take that to be 175 kilojoules. We'll divide it by the 17.4 kilojoules per mole. And the last thing that we need to do is to multiply by the molar mass of the difluoromethane. So we've got 19 for fluorine times 2 plus 2 times 35.45 plus 12.01. So I'm getting 120.9 grams per mole for the molar mass. And then we'll run these numbers through our calculator, and that'll tell us what mass of this refrigerant do we need in order to freeze this water to ice. So I'm getting a mass of 1,216 grams out of that calculation. Here it looks like this problem is similar. It's just you're using a different refrigerant. You're using ammonia, I believe. No, you're using ammonia. So I'm going to leave this one as an exercise for you guys to try. Here, this problem is a heating curve type of problem. So this one's a bit different. They want to know how much heat is required to convert 135 grams of ice at negative 115 degrees Celsius into water vapor at 120 degrees Celsius. So what you need to do to calculate the total heat, first you need to calculate the heat for heating the ice. And so I'm just gonna add these terms in. So what we're going to need to do is take the mass times the specific heat of the solid ice times the temperature difference between the ice at its initial temperature and the boiling point of, the melting point of the water. So we're going to go from negative 15 degrees Celsius as our initial temperature of 258. And what we're going to do is we're going to heat that up to the boiling point, the melting point of water, which is 273. So this is mass times specific heat times the temperature difference. You know what, maybe I'll write it symbolically first. That'll make it a little easier. So we'll take mass times the specific heat of the solid, and this will be the melting point minus the initial temperature. Okay, so this is going to heat us from the ice at minus 15 degrees Celsius to the melting point. Then what we're going to do is we're going to melt that ice, and so we're going to take it times the enthalpy of fusion for the water. So this is going to take us from the initial temperature to the melting point. This is going to melt the ice. Then what we're going to do is heat up the liquid water. So we're going to go from the melting point all the way up to the boiling point. Then what we'll do is we are going to boil the water. So we'll multiply by the enthalpy of vaporization times the number of moles. And then finally, we're going to heat up the steam. So the specific heat of the gas, it'll be our final temperature of 120 degrees Celsius minus the temperature of the boiling point. Okay, I'm going to go ahead and flip back to the graph just to illustrate what we're doing. So we're starting down here somewhere. That's our TI. And then we're calculating the heat associated with heating up the ice up to the melting point. And then this term right here, this corresponds to the heat required to melt the solid. Then this next term corresponds to the heat required to heat the liquid up to its boiling point. Then we calculate the heat associated with boiling the liquid. And then here we have the term associated with heating up the steam. Okay, so what we need to do is to basically plug all of the numbers in here. This video is getting a little long, so I think I'm just going to leave that as an exercise for you to try. But here I've listed out all of the parameters that you need. I think the only thing that you need to do is to calculate the molar mass of the ice, or of water, and plug that in there. So I'll leave that as an exercise, and I'm going to go ahead and stop this video right here.